Hello and welcome to Lecture 5 of Work and Energy in Electrostatics in Phys 1204. In this video lecture we're going to look at how we can make a connection between electric potential and electric field, and on the way we're going to see Kirchhoff's loop law, which is one of the most important laws for circuit analysis. We're going to get more quantitative about some relationships we already saw in Lecture 2. In that lecture, we saw that if we connect any two points that are on the same equipotential surface by a path, the electrostatic work along that path must be zero. And that tells us that the electric field is perpendicular to the equipotential surface, and so field lines are always perpendicular to equipotential surfaces. Also, a positive probe charge must be speeding up as it moves from high potential to low potential because it's losing potential energy, and so the field must point from high potential to low potential. This last thing is actually something we saw way back in Phys 1104, because there we saw that for non-dissipative forces, the force always points from locations of high potential energy to locations of low potential energy. And since high potential is where positive charges have high potential energy, we see that this is just a special case of that rule. So suppose we already know the E field as a function of position, and it can be any E field. So what I've drawn is some sort of arbitrary set of field lines. And we have some point A and some point B, and we're thinking about a charge that's moving along a path from A to B. Then we know that the work, the electrostatic work from A to B, by definition is just an integral of the electric force dotted with the displacement elements. And so because that electric force is just the electric field times the charge on the particle that we're moving around in the field, that gives us that the work is related to an integral of the E field dotted with the displacement elements. Now note that the potential difference from A to B is just the negative of that work divided by the charge. And so that shows us that if we just divide out that charge, it disappears. We get that the potential difference from A to B is directly related to the E field by an integral along the path of the E field dotted with the path elements. So this gives us a way of finding potential differences in the case that we already know the E field. And realize that you should save effort. You know that this integral has to be path independent. And so if you have a choice, you should always try and use a path that will make the integral the easiest to do, not necessarily the actual path that, say, a particle might be following from A to B. Let's use this relationship between potential difference and E field to find the potential difference between one plate and the other of a capacitor. So here is a capacitor. It's been hooked up to a battery, which caused it to become charged, and we now know that there's a uniform E field inside it, and that's going to make it very easy to find the potential difference between the plates. So the plates have some separation S, and the first thing I need to do is define a path, which I've done here from A to B, A on the positive plate, B on the negative plate, and I've made sure I've picked an easy path. In particular, it's parallel to the field. Furthermore, I'm going to define axes. I am going to put my origin on the positive plate with my x-axis pointing from the positive plate to the negative plate. And so now I know that the E field is parallel to the direction I'm going here, and so this is an E dr cos theta, but theta is 0, and so the cos theta is just 1, and I'm just going to have E and the size of dr, but I'm going along parallel to the x-axis, so I can just call that dx. And so I'm now integrating with respect to x, and I'm going to do it from 0 to s. And that's going to be very easy because this E field magnitude here is a constant, and so it just pulls out front. And so I have one of these easiest integrals in the world. And so we see that the potential difference across the plates is proportional to the E field. And in particular, if we keep the same E field but change the plate separation, then the potential difference is proportional to the plate separation. Let's use this to do something else. Let's say we have an arbitrary point P inside the capacitor, and we want to know the potential there. Now, what we're really doing is finding the potential as a function of position inside the capacitor. And so, in particular, this point P is at some point that has an x-coordinate that we'll just call x. And so again, I'm going to define a path over to the other plate where I'll put a point Q. And I've again gone parallel to the field to make everything easy. Note, the value of potential is arbitrary because where the potential is 0 is arbitrary. And so I am going to define the potential to be 0 on the negative plate. There's no reason I couldn't define it to be 0 on the positive plate or anywhere else, but the negative plate is going to be convenient. And so now, again, I can say my delta V from P to Q is going to be, and it's going to play out in exactly the same way. I'll write P to Q, but again, E is parallel to dr, and so this is just going to come out just like it did before, but we're now going from the location of P, which I said is just some x, to S. And note that what we actually wanted was the potential at P. Well, the potential difference from P to Q by definition is just the potential at Q minus the potential at P, but I just defined the potential at Q to be 0. That means V at P is just the negative of all this, or in other words, E S minus X. And in particular, what this is showing us is that the potential is linear in between the plates. It has a slope of negative E and has a value ES at the positive plate, under this assumption that V is 0 on the negative plate. And I want to particularly draw your attention to the fact that the slope of the V versus X graph is negative E. That is very important, as we'll see. Let's come back to very general cases. So here are our points A and B in some arbitrary E field, and let's think about two paths, 1 and 2, that connect points A and B. Well, the electrostatic work is path independent, and so the work along path 1 has to be the work equal to the work along path 2. Note that that means that the work along path 1 is the negative of the work along path 2 if we go in reverse from B to A. Notice that from A to B along 1 and then B to A along 2 is a closed path. And so what we have is that the sum of these two works around the closed paths is 0. But this is totally general. This is just something that's happened because we know that electrostatic work is path independent. And so it must always be true for any points that form a closed path. The electrostatic work around any closed path has to be 0. The fact that electrostatic work around any closed path is 0 has consequences for potential difference, and it's going to be a particularly useful consequence. Since the potential difference is just the negative of the electrostatic work along the path divided by the probe charge, that tells us that the sum of potential differences around any loop is also 0. This is something that is called Kirchhoff's loop law, and it's completely general. The sum of potential differences around any loop is always 0. And although I've been drawing it for seemingly empty space with E fields in it, where this law actually comes into its own is in circuit analysis, where it turns out to be very useful for finding potential differences across devices within a circuit. Here's a simple question to check whether you're understanding the loop law. So here is a set of points, and a path is indicated from A to B to C to D and back to A again, and so that is a closed path. And the potential differences that would be measured from A to B and B to C and D to A are indicated, and all you have to do is figure out what potential difference must exist between points C and D.